Hello everyone, I am Pawel. I work in Google in Operations Research Team, and today I'd like to give you a high overview of combinatorial optimization at Google. What kind of problems do we encounter and how do we address them? So the outline for this talk is pretty straightforward. I'm gonna start with introduction, giving you some high-level overview and some examples. Then I'm going to focus on just one example and do a deep dive, showing you step by step how a particular problem would be addressed at Google. And I will spend the rest of the talk by discussing some benefits and challenges of using principled combinatorial optimization techniques to solve problems in the real world. So let's start. So what is combinatorial optimization for the purpose of this talk? So this is any sort of LP, MIP, so linear programming, mixed integer programming, constraint programming applied to scheduling or vehicle routing problems, and some specialized graph algorithms, graph problems, like for example min cost flow. So these are the domains we are mostly interested in. So this talk will not be concerned with, say, stochastic optimization. For all of these domains, at Google we have specialized solvers. So we have LP, MIP, SAT, CP, VRP, graph algos. We have all of that. And as a matter of fact, we actually open source all of these things. And there was a different talk which I gave a few days ago on so-called OR tools. And I encourage you to look at that because this is the library, the framework for solving combinatorial optimization problems that we use at Google. We use like our internal version, but it's fairly the same. So I encourage you to have a look at that. But now let's move on to problems at Google. So one application for which combinatorial optimization is used is for image stabilization, as you can see on the video here. This is solved by solving linear programs that try to stitch together the images, the consecutive images. We use combinatorial optimization to optimize our data centers. We optimize many different aspects, compute, storage, networking, cooling, all sorts of things. We use one of the first application of combinatorial optimization at Google was routing street view cars. So deciding how the drivers should go through the streets of every city in the world to map the world. And some other example, maybe less known, is also loon balloons. We use combinatorial optimization. We use min cost flow algorithms to control a cohort of balloons. So this was just very a sneak peek on different applications in which Google is using combinatorial optimization. Let's now just focus on one abstract example which will give you an intuition what it means to solve combinatorial optimization problems in real life. So I will be focusing on an example of a MIP model. So just to ensure we're on the same page, this is a MIP. So you have an objective value, which is an affine combination of the variables and a direction subject to linear inequalities. And then the variables are bounded, and so the bounds can be infinite, so it doesn't have to be bounded on both sides. And then there is some set of variables which are set, they have to take only integer values. So this is a MIP, and I will be using this as an example. So imagine that there is a problem. You have to place items into containers. So this really is a very often met problem in practice, at least at Google. We place many different things into other things. So for example, here you could think of those elements, of those items, as being jobs that service a file. Okay, so it's not only a file, but it's actually a process that serves a file. So this is a thing which consumes some resources. It consumes CPU, it consumes RAM, maybe other resources. And then you want to place those items into containers, say machines. So machines contribute the resources, and you want to find a placement of these file serving jobs onto the machines. So how to best model this, how to best approach this? So in our practice, mixed integer programs are really nice for this kind of problems. So what is the problem first, right? So you have the indices of the problem. You have items indexed by I from 1 to big I. You have bins, so containers, indexed by B, and you have multiple resources. And then you have some input data called constants. So you have how much resources required by every item, so how much CPU this item consumes, for example, and you have how much resources available in every bin. So now you want to place items into bins, so you need a variable that does this. So you have a variable place IB, meaning place item I in bin B, and this is a binary variable because you can either place an item there or not. Then you need the constraints to link everything together. So first of all, for every item, the sum of the place variables across the bins have to be equal to 1. This means that you place each item exactly once. And then for every resource and for every bin, the amount of consumed resource at the bin, so this is just a sum over all placed items times how much resource it consumes, has to be lower or equal than the amount of resource available in that bin. And if you just have this is a very basic model, but this is like a multi-dimensional multi-packing, that you have multiple items that are multi-dimensional and you have multiple containers of the same dimensions, and you want to place everything somehow. And this can be modeled as a MIP, and if you do this, this is what comes out. So you could imagine that there is a team, there is a product that needs such a functionality. For example, a system that assigns jobs to machines needs such a component. You could implement this as a MIP. Then what often happens is that it turns out that the problem is more complicated, so there are extra features which you need to support. So for example, here, at some point it might turn out that you not only have single jobs or single files, some of them can actually be replicated. So you have redundancy. So you want to place multiple copies of the same items simultaneously. Now the nice part about MIP is that if you have your initial MIP, very often to add a new feature like that, it's just a matter of few changes. So in here, of course, you need the extra input data, which is the number of copies of each item. But then the only change you need to do in your algorithm is to say that the variable is no longer binary, but is a generic integer. And then, in the constraint, you have that here equals to the number of copies, because you have to place all of the copies of each item. By the way, I encourage you to hit pause anytime you want to spend a bit more time reading these formulations. I think it's very useful if you find time to actually understand them well. Now in real life, features just keep coming in. So at some point it might be that, well, this is a real life system, so you'd like it to be fault tolerant. What does it mean? It means that the placement on the left is not good, because copies of the same item are all placed in the same container. So if this container malfunctions, you lose all of the copies. So what you would like to have is to spread the copies across the containers, or at least disallow keeping the copies of the same item in the same container. This is even a simpler change in your model. Now you just revert the variables to being binary again, and this will automatically ensure you that on every single bin, each item will be present at most once. So at most one copy of an item will be kept in a bin. As said, this is real life. Features just keep coming in. Another quite often observed requirement is when you place items into containers, you would like to have a balanced placement. What does it mean? In here you can see that you have 3 items in container 1, 2 items in container 2, and 1 item in container 3. So it's 2, 3, 1. It's imbalanced. This container contains, half of the items in this particular example. This is not good because this makes the system to be imbalanced, so some parts are more used than others. Often what we would like to have is that the placement of items is evenly spread across the containers. Now the question is how to do this in a MIP. This can also be done. You define extra variables, which are continuous variables, which I call the surplus, and these variables will track, will compute how much above the perfect expectation, how many items above the perfectly expected are there in every bin. So for every bin, you create a constraint, and let's look what it is. So the sum across all items of the number of copies, this is just the total number of copies. This is divided by the number of bins. So this thing here is the number, how many items you expect per bin in a perfectly balanced situation. And you subtract it from the actual number of items placed in a bin. So what the left-hand side represents is the surplus of items in bin B above the perfect expectation. And you upper bound it by our continuous variables, which you then minimize. So you push from above. You want to make the surplus as low as possible. And this will implicitly lead to balancing your placement. And then one final thing, which often happens, is that, well, this is Google, these are real life systems, they exist. So often when you want to find a placement, it's not any placement, but there is already some placement in place, let's say, because the system is operating continuously. And you want to find a new placement which is just a bit better, but not really different from the current situation. So this is depicted here that maybe you would like to pin those files, saying, okay, you shouldn't really move those because this would incur too much change to the system. So how can you do this? This is just one way of doing it. There are many, but let's say that you know how many items you are allowed to change in a single iteration of the system. And then you of course know what is the current placement. So if you just add this sort of constraint here that iterates over all bins and all items and computes this is a linear equation. This just counts how many items have been moved, and you upper bound it by the number of allowed moves, and that's it. So what happened here? In just a few steps, in like 5 minutes, we went from just placing items in bins into multi-dimensional multi-packing with redundancy, fault tolerance, balancing, and reducing churn. And this really depicts how it happens in practice. When you develop your your combinatorial optimization solution, your operations research solution to a real-life problem, often new features will appear in a sequence, and using mixed integer programming or constraint programming, any sort of declarative type of programming, allows you to iterate quickly and have a very nice solution. So this actually leads me to next chapter of my talk, which is about the benefits of using mixed integer programming, or in general any type of math programming which is declarative in nature. So normally what happens when you are a software engineer and you face a problem, you define your inputs, you define what sort of actions need to be computed, and then you have to write the algorithm. You have to decide what to do and how to do it. So this is called imperative programming. But with combinatorial optimization, with math programming, what you can do is that you abstract your problem into a model. And this is just a description of your problem, just like we did in the example, right? We described what we want with variables and constraints and objectives. And that's it. We don't have to solve it because it's being solved by a black box solver, a MIP solver, a CP solver that you as a client, you as a user, you don't have to know about. You just want to use it. So that's why it's very nice to use these techniques in industry, because they allow you to very efficiently create a declarative description of your problem, and you don't need to deal with the implementation details. Another nice thing about combinatorial optimization and MIPS and CP in particular is that they are relatively minimalistic. So for MIPS, for example, all you have is variables, bounds, and linear equations, and that's it, right? And so the language, the syntax is very small, and yet it's very expressive. You can actually express all of those different things that I showed in the deep dive. What's also nice is that it's modular. So you have the constraints are kind of grouped into families. So you have a family of relating to my example, you have a family of constraints related to keeping sure that you place all of the items, to keeping sure that the capacities are not overconsumed, to actually balance the placement, and then to make sure that we didn't move too many items. So it's really modular, and when you code this in your code, it's also modular like that. So it's clean, readable, easy to test. And last but not least is that it leads to encapsulation. So if you went the route of imperative programming, so you actually code the algorithm yourself, then what would happen over time is that new features coming in, new sources of inputs coming in, and your algorithm becomes very convoluted. You have many if-else statements for various corner cases, and at the end of the day, no one really fully understands how your algorithm operates under all of the conditions. Whereas if you use a MIP or a CP, this is not the case, because you are forced to abstract all of your problem into the model. So you have to put all of the input data into the model, which you then send to the black box solver that might produce various different actions. And this separation between model and solver sort of extends into your system and makes sure that your entire system stays modular, and that the modules are encapsulated nicely. And this again leads to a very healthy, very easy to maintain code, and this is extremely nice from engineering perspective. So let me just finish by showing some challenges that you might encounter. So this is a part in which I will try to explain what is needed to achieve success in applying combinatorial optimization in industry. So first of all, the first challenge is to meet the client. So this is sometimes hard because you don't know who is responsible for the system. But once you get a good contact in the product or system that you would like to improve with combinatorial optimization, you of course need to define what is the scope of the project, what is needed, and then potentially prototype something to show the client that there is a premise of improvement. Then, assuming that the client is happy, you start actually solving the problem. So you need to collect the data. Very often you need to clean up the data. And this part is often very, very hard because data might be kept in various sources in different formats. You have to unify everything and make sure that the data is actually correct. Once you have that, you implement your optimization model, You run it on your data, and you might need to verify something. You might notice that it's not that efficient. Maybe you need to remodel, or maybe you actually discover that the data is not clean or not correct. So then what happens is you have to iterate. So once you verify the solution, you might go back to the implementation, or you might go back to the collecting of data, or you can actually go back and redefine your problem. And this happens very often. Very often clients don't have a clear understanding of what they really want. What are the metrics they care most about? They just say, well, we would like our system to operate, or like, very vague and abstract metrics. And with MIPS and CP, everything gets boiled down to equations. So you have to be precise. You have to precisely define what are all the goals and all the constraints in your problem. So this sort of loops can happen, can repeat many times. And the most crucial part is redefinition. So to work close with the client to update the specification for the system, and this collection of data. This is really important. Then once you actually have iterated enough and have an implementation which is deemed sufficient, then you land your product. So you deploy your combinatorial optimization solution in the actual system, and then you monitor it for a while to ensure that it actually works as intended in real life. Often it actually does, because here you made so many iterations that it really does work as you intended. And then in the end, of course, you have to maintain this product, this part, and this might require you to add extra features sometime in the future. When the system gets mature and the combinatorial optimization part is there for a while, the client team might come back to you and say, well, now we want this extra feature, and how we can include this in the optimization model that you have created. And just so you know, in terms of timing, this initial phase of project discovery, this is, I would say, around a month. Of course, this depends greatly on the project, but let's say it's a month. Then this part of solving, so this iteration loop, this might be well above a year. Then once the product is ready, landing it is relatively simple. Let's say 3 months of work, and then maintaining, of course, it's like forever. Hopefully you would like to educate your client so that she or he can actually add new features without your help. But if the optimization model is really complex, then the client doesn't have optimization expertise, so you might need to help them out with that forever, or for the lifetime of the project. And just one last slide in terms, if you're interested, how much time you spend in different aspects when applying combinatorial optimization to real life problems. Half of the time is just this discovery phase, this discussion with client, discovering and defining the features and the scope and the requirements and the objectives, and redefining them and making them clear. This is just over all the time spent on the project. This is like half of the time. Then other half is implementation, but from this implementation, really half is like getting data and cleaning data and understanding data. Then coding the actual optimization model, this is fairly simple. This is really quick. To code up a mixed integer program, you just need like, a month of work, maybe not, maybe even less. So this is really quick. So I would say like 10% of your work is on coding. And then again, once you have the model in place, you have to explain the results you obtain from your combinatorial optimization algorithm back to the client, so he or she understands precisely what is happening. So that's it. I hope I gave you a nice overview of what it means to apply combinatorial optimization in practice, at least in Google. I hope that I convinced you that mixed integer programming and constraint programming, and in general any sort of declarative programming. It's really nice because it has all of this engineering, it brings all of these engineering benefits. And at the end, I also wanted to give you a glimpse into how a real life project, how a timeline would develop when you want to apply combinatorial optimization to real life problems. At the end, I also encourage you to have a look at our link, developers.google.com/optimization. There are many interesting materials there. Yeah, and see you on the Zoom session. I hope you have some interesting questions. Bye.